Hello everybody. So now we are back to our teaching mode, and we will try to continue basically in this course what we have started before. If you go back to the last video that we recorded in chapter 1, we were going through some introductory parts on the light interaction of light with matter and the discoveries made in that direction. Now, today, in this video, I will basically continue on this to finish it, and there will be a remaining part in chapter 1, which is basically applicable, meaning that all the exercises that we will solve in chapter 1 will be based on that part. I will record it in another video just after this one, so that you have the parts in separate videos. So if you go back to the last video, as I said, you will see that we were talking about the black body radiations. And we said that a black body is a body that has an emissivity equal to 1 and an absorption coefficient also equals to 1, which means that this body would absorb all the light that comes to it and would also emit all the light out of it. And the interest of the scientific community at that time was that when you heat a black body and you raise its temperature, it actually starts to emit light that the color of which depends directly on the temperature. So the more the temperature is increased, the color of the light that is emitted tends to go towards lower wavelengths. And these are the curves that you see here. These are curves that I calculated actually just based on the formula for different temperatures, and you see that the more the temperature goes up, the maximum of the emission, this is the intensity of the emitted light versus the wave number of the light color, well, the maximum shifts towards lower wave numbers. Now, the interpretation of these experimental spectra dazzled physicists between the 40s, between 1860 and 1900. Now, Stephen Vane and Relay and Jeans are the most known scientists or physicists who treated this subject, but unfortunately their outcome was wrong. They actually looked into describing the distribution of the spectral radiation as a function of the wavelength or the wave number. And as you can see here, Stefan suggested actually that it's proportional to the fourth order of the temperature, and this is based on statistical thermodynamical interpretations. Wien predicted, actually using also thermodynamics, that the peak of the maximum actually is inversely proportional to the temperature. And Wien suggested this relation for the spectral distribution or spectral radiation of the emitted light. The most known interpretation of these black body radiations is by Lord Rayleigh and Jeans. Actually, they considered the following, that when you heat a body, then you will actually create more oscillations of the small dipoles which forms the molecules inside this body. So these molecules will start vibrating back and forth, back and forth, back and forth, and forth. And when they vibrate at a given frequency, they will emit light at this frequency. And the frequency that they have calculated, which is c over lambda, they say that the energy of each oscillator could actually vary between 0 and infinity in a continuous way. And this gives this solution or this expression for the spectral distribution. Well, in fact, the problem with this expression is that it scales with the temperature. Although it can explain the shift of the peak when the frequency with the temperature, it shows that the peak goes towards lower values. But the main problem with it is what the community called the ultraviolet catastrophe, is that if the temperature goes up and up and up and up and up, then the distribution peak will go higher and higher and higher towards the ultraviolet, because it will shift more and more and more towards lower value, and it will become in the ultraviolet, which means that if we heat something extremely high temperature, it will just emit in ultraviolet, which is a catastrophe. And this is obviously was wrong, because it did not fit basically the experimental data. So the colored curves that you see here are experimental data. So it's a measured distribution emitted by black bodies. However, the black line is this expression. So it's a theory. And we see that, well, this expression actually does not have a peak, basically. It increases in a continuous way. Now, obviously, this comes from the fact that these guys considered that the dipoles can oscillate with energies that are continuous. So the solution of this comes with a bright insight by Max Planck. Well, Max Planck suggested that these oscillators that Rayleigh and Jeans talked about, they actually cannot have continuous energies between 0 and infinity. So they are vibrating, that's correct, but they can only take, their energy can take given or discrete values. And these amounts, which is n epsilon 0 or E0, since E0 actually is a finite amount of energy, which he called quantum, from the Latin quantum, which means how much. And mathematically speaking, the spectral distribution, the expression of it, he found it to be written in this way. So it shows that the peak goes down, but actually it fits perfectly well the experimental data. So this mathematical expression is correct. And the physics behind it needs actually to satisfy the displacement law of Wien's, which goes with the lower values for the wave number, that this amount of energy should be equal to hc over lambda, or h nu, which is the quantum that you know now. Now you know that a quantum of energy is h nu, but this is where it comes from. And h is a constant that Planck found to fit all his data, and this is called the Planck's constant. So this is the quantum of energy, and this is the entire concept of quantum mechanics afterwards starts from here, that things or energies cannot be emitted necessarily in a continuous way. They are emitted in a discrete values with a smaller amount of h nu. Now Albert Einstein took this idea and extended it to explain the photoelectric effect. Now the photoelectric effect, for those who do not know that, is actually, it has been observed when you have two metals, a cathode and an anode, put in a vacuum chamber, and when you send light into the cathode, sometimes with an ammeter you can measure current, which means that there is electrons going through the vacuum between the two plates and closing the circuit. And if they change the light, so the wavelength of the light, say it's red light instead of a green light, for example, then there is no current, which means there is no electrons going there. Even if you increase the intensity, so you put a lot of red color, this changes nothing. If you put back a little bit of green color, then the current appears. So clearly this phenomenon is dependent on the wavelength of the color, of the light. So after Max Planck has found this relation of the quantum of energy, then the breakthrough of Einstein, and actually this is the story for which he received his Nobel Prize, by the way, is that he said that light is made of small energy particles. Each one of them has an energy equal to h nu. Nu being the frequency of the light wave, because before that it was known internationally that light is a wave. Although it was not known necessarily what type of waves it is, or was it? I think it was known that it's an electromagnetic wave, but it was not known that it's a particle. And the explanation of Einstein was to say that it's made by photons, which are massless particles, and they are just energy. And so that if the energy h nu of this photon coming into the metal, if it's equal or more than phi being the work function is the energy that you need to give to an electron inside the metal to get it out of it. So if the light has an energy, incident energy, that is larger than that, what happens is that the metal absorbs this energy from the light, gives phi to the electron to get it out, and then the excess of energy is taken by the electron as a kinetic energy, which makes it travel in vacuum to reach A and then close the circuit. Okay, so just one note on this. Notice that Einstein said in his suggestion that the photon of light has an energy equal to h nu. If we go back to Planck explained that this h nu, which is the minimum amount of energy, is the discrete energy of the vibrating oscillator that Rayleigh and Jeans talked about. And if you combine these things in your mind, then you can think about what I will just say now, that the photon basically is a small vibration of the electromagnetic field. It's like the electromagnetic field is oscillating, basically, as an oscillator, and this oscillation of the electromagnetic field, it shows up as a small amount of energies, which are the photons. Okay? Think about that. Now, once Einstein made this and proved it, Compton, Arthur Compton is another British physicist, made an experiment to actually prove this particulate nature of light, of photons. So it was a suggestion from Einstein that light is made of particles of energy. Compton tested that hypothesis. He actually positioned an electron and sent photons to that electron. So these photons that he sent, let's call them incident photons, they have a known frequency, so a known energy. They hit the electron. And the outcome of this is actually extremely similar to a collision between two particles. So the electron actually scatters, so it is pushed in another direction with a certain energy, and the initially incident photons, they scatter also So it's like the particle of the light scattered, but it scatters actually with a different energies because it lost part of it, so a different frequency. So he could actually hit an electron, detect it at a different angle, which means it has scattered, and then detects the light after this collision, which is at a different frequency. So this proves basically that light really can act as particles, and this gives it the property of having a momentum. However, as you know, momentum is something that is given for mass particles. So particles who has a certain mass, they actually have a momentum, P equal mv. While for a particle which is a massless a light which is a massless particle, there is no mass. So how could it have a momentum? And basically the work of Compton is to say that the momentum of photons is directly dependent on the energy and is equal to h nu over c. So this is the momentum of massless particles like light or like photons. Now at this stage of history, if you want, light is the only physical entity that has two natures. It has a wave-like nature and a particles-like nature. In some phenomena, light acts as a wave. In other phenomena, light acts as a particle. Right? Now, I don't know which year, but from France, Louis de Broglie, who actually, as I know, he has studied geography, but he wasn't an aristocrat, so he had money, and he had a lab in which he was trying to study radio waves on the top of Eiffel Tower. And he was interested in reading physics, obviously. So he made a PhD in which he suggested the following. If actually photons are known to be waves, but could act like particles with a certain momentum p equal h over lambda, then why not, and this is de Broglie idea, why not consider the inverse? So if we have a particle like an electron that has a mass and has p equal mv, why not we associate to it a wave nature, and that this electron or this particle also has a wave number or a wavelength. And so he came up with this relation, so p equal h over lambda equal mv, which means that every particle will have an associated wave to it that has a wavelength lambda equal h over mv, v being the speed of the particle, m its mass. And Einstein was struggling to find something interesting about quantum mechanics, and when he read the thesis of de Broglie, he asked to meet him because the idea was extremely interesting. And Schrödinger, where is it? Well, I have skipped it, but I will use it here. Schrödinger basically used the idea of de Broglie to say that if there is a wave that is associated with an electron, then he came up with an equation that describes the electron as a wave. And this is called the wave function of an electron. Okay? And It's the famous Schrödinger equation, which is the, if you want, it's the equation of motion of the wave function of an electron. So it tells us basically at which energies we can find this electron and how it's going to evolve in space and in time. Now the expression that you see here, it's time independent, so there's no time variation here, and it's in only one dimension, x. But obviously you know it from quantum mechanics how to do it in 3 dimensions. Now after the discovery of de Broglie, it's not necessarily after in terms of history, but as a subject of interest, it has been shown by Newton first and then by Melville that we can actually disperse light. This is Newton's prism experiments, that we can disperse light into different wavelengths, so different colors. And this is the experiment, the famous one. If you send the light of the sun into a prism with a given angle, then you will see actually at the output different colors. So you splitted the light into different wavelengths. But later on, it has been shown that a gas that is heated is composed of different frequencies of light, so different colors, and they are called emission lines. So it's as if this heated gas is emitting light at different colors, also at different frequencies. And the most important discovery was made by Balmer, and I think you have seen that in atomic physics. Balmer showed that atomic hydrogen, if it's excited, it actually go to the ground state by emitting very specific colors, so light at very specific frequencies. And he came up with this relation that the frequency of each line could be written actually with this formula, where NA and NB are numbers corresponding to the states. So it's as if from the transition from an excited state of the hydrogen atom to the ground state or to another state, there is a light emitted at a given frequency. And this constitutes actually the main problem for Niels Bohr to solve. So Niels Bohr did not look into how to create quantum mechanics. He was looking into how to explain Balmer's emission lines. But while doing that, he came up with a huge theory of quantum mechanics. So the solution from Niels Bohr, which, as also you know, is not the accurate one after all, but it's the very good one to start with. So Niels Bohr was the student of Rutherford. Rutherford, if you remember that, is the New Zealand scientist, physicist, who used to work in Cambridge, in the Cavendish laboratory in Cambridge. And he was the one who discovered that the atom has a nucleus and that electrons are traveling around the nucleus, and there is a lot of empty space between the nucleus and the electrons. And this is the first time in history that what we call the nuclear model of atom has been suggested, and this was by Rutherford. This is the famous experiment where he actually put a gold foil sheet and he sent alpha particles to it and then looked into these alpha particles when they are transmitted through the foil and bounced back. And this is where he realized, after 1 or 2 years after receiving the experimental observations, So the analysis took almost 2 years. He came up with this nuclear model where he said that there's large mass of the atom is concentrated in a part that he called the nucleus, and that this part should be positively charged, and that the electrons are floating around this nucleus part, and there is a lot of empty space in between. Now we're not going to go through this because that's more in the atomic physics, but the Rutherford model was not totally correct. Niels Bohr was his student, so he wanted to explain the emission lines of the hydrogen atom observed by Balmer, but obviously he would start from the work of his professor. And he improved on it, he corrected it. Bohr made several postulates, several assumptions that we're also not going to go in this course into them. But if you're interested, I can talk more about that in the course that I have given on atomic physics. But basically Bohr said that the electrons actually travels around the nucleus in circular orbits. This was one of the postulates, and this is only made because it was mathematically easier. The other postulate that he made, that they go in stationary movement, which means that they have an associated wave to them, but this wave is stationary, meaning that they can have just a specific energy at each orbit and none in between. These are the postulates that he started with, but these postulates actually were able to explain all the experimental observations on the hydrogen atom. And so he made his model of the hydrogen atom the known model of Bohr. And he said that the frequency of the light that will be emitted from an atomic hydrogen is actually proportional to the frequency of the light that is, it's proportional to the difference of energy between two orbits of the electron, so two energies of the electron. And this is the known formula that you know. I believe you should know that. Okay, great. We talked about Schrödinger. Now, all this was mostly about atoms, but our course is more about molecules, and molecules contains several atoms. And what we are interested in is to look into the energies of these molecules inside a gas or inside a liquid or inside a solid. And so the Born-Oppenheimer approximation states that the movement of electrons is separate from the movement of the nucleus. And so we are going to consider mostly that the nucleus is much heavier than the electrons, and that the nucleus does not necessarily move. And so the energy of the molecule is basically characterized by the energy of the electrons. But these energies have different types that we will call the electronic energy, E-electronic, the vibrational energy, and the rotational energy. As we will see later, each of the energies here will be in a chapter. We are not going to talk about the electronic one. We are mostly going to talk in details about the rotational energies, vibrational energies, and the combination of both. So you will see that we will be talking about En, n being a quantum number that actually describes the electronic states, E nu or EV, which basically is the vibrational energy states, and Ej, which is the rotational energy states. Now, as Bohr said, that basically light will be emitted or absorbed when there is a change in the energy of the electron between two different orbits. Now, in a molecule, as we said, we don't have only one atom. So basically, it's when we have absorption or emission from a molecular gas, it means that the difference of energies is between two different states, either two different electronic states or two different vibrational states or two different rotational states. And we will see this in more details. But they are of different order of magnitudes. So the higher one is the energy of the electronic states, which is in the electron volt regime. And this is in the UV visible range. If there is a change of the vibrational states, this will emit light with an energy 1 of the tens of electron volt, and this is in the infrared emission or absorption. Okay, so if something is emitting light in the infrared, it means it's a vibrational energy of a molecule. And you can now relate things together from what we said so far. Remember that we said that when we heat something, we are creating more vibrations of the oscillators. And also know that when, for example, people use infrared vision or night vision goggles or systems or cameras, the infrared cameras, they detect actually the temperature of bodies, which means that it looks into the energy of the vibrating oscillators inside matter, or the light emitted by them or absorbed by them. So this is why the change of the vibrational states will emit light in the infrared region. As for the rotation, it's in the microwave region. And this is really the microwave that you use to heat food. Basically what you do is in the microwave you are emitting waves or microwaves, so they are in the region of energy of 1 over 10 hundreds of electron volts. And these microwaves are absorbed by molecules, especially water molecules inside food or liquids, and they will make them rotate faster at higher states. So the rotation of these molecules at higher energies heats the food or the water. So instead of raising the temperature to heat the food, you just rotate its molecules faster with a microwave. Okay, that's as simple as it is. Here is an example of the diagrams that we're going to use a lot afterwards in the following chapters, but it's just to give you an idea about the different contributions of the electronic levels, of the rotational levels and vibrational levels. Now you see, the electronic level is defined by a quantum number called n. So say for the fundamental electronic level n equals 0, then the molecule that we're talking about could have different vibrational energies. So it could be vibrating possibly at different energies, and this is characterized by the quantum number v. So you see that v equals 0 is a one vibrational energy state, v equals 1 is another, v equals 2 is another, and also it could have different levels of rotational energies, j equals 0, j equals 1, j equals 2. But you can see that the differences between these energies of rotation is much smaller than the differences between two levels of energies in the vibration states, which is also all of them much smaller than the difference of energy between N1 and N2. So an electron can occupy a position on this line and then do a transition to the line just below it, or to the line in a different energy of vibration state, or a line in a completely different electronic state. And all this is based on several rules, and this is what we will basically learn in the coming chapters. As you see here, for example, these are two states of a molecule. It's a molecule in the electronic state n equals 0, the vibrational state v equals 0, and the rotational state corresponding to the number j equals 0. If it absorbs light, it gets excited and go to another state, but you see from the quantum numbers, the only thing that is changing is the rotational j number, which means it's just a transition into a higher rotational energy state. So the molecule is rotating with higher energy. And in this case here, it's the opposite. So if it was rotating at higher energy, if it emits light, it actually loses energy and starts rotating at a smaller energy. Okay? The minimal condition of this to happen is that the difference of energies should be at least equal to h nu, which is either the light that is absorbed or the light that is emitted. So the transitions, this will be mostly the thing that we will be talking about in our course, is the transitions between energy levels. Why transitions? Because we cannot know anything about the gas or the liquid or the solid that we are studying in physics experimentally if this substance does not absorb light or emit light. Because absorbing light or emitting light is the way we can talk with matter. So if we send some light and it absorbs it at specific energies, we know something about it. If actually we excite it and then it emits light at specific frequencies, we know something about it. But if it does nothing to light, then we cannot tell what it is. So all is in the interaction, and the interaction always is either by absorption of light, so the molecule goes to a higher state, or emission of light when actually it transits from a higher state to a lower state. And in both cases, what we measure experimentally is a spectrum, which tells us how much of the light has been absorbed at given frequencies or wavelengths or wave numbers. And this is called absorption spectra, or it's an emission spectra in which actually we see at which frequencies or wavelengths or wave number the emission of light has been higher for this molecule or the other. So we have the rotational transitions. It's between two states that they have same n and same v but different j, and we see that before. And it's in the microwave domain, and it gives us line spectrum. So the spectrum is just made by lines. However, the vibrational transitions are between two states that have the same n but different v's. So different number v, which means different vibrational states. The light emitted or absorbed in this transition is in the infrared. So what does that mean? It means that if you send an infrared light to a molecule or to a gas, and then you see from the spectrum that it has been absorbed, or part of it has been absorbed, it means that you contributed to change the vibrational state of the molecule, because your light is in the infrared. However, the spectrum that we obtain is not made by specific frequency lines, it's made by a band. So we call it a band spectrum. So it's different numbers of frequencies. Electronic transitions, it's between different states of different values n, and it emits or absorbs in the ultraviolet domain because it's much higher energy. As a summary of these transitions, what you can see is that if you are talking about molecules, then there are several physical processes, either the rotation of the molecule, which actually give us a spectrum in the microwave regime, and the name that we give, it's either a rotation spectrum or a microwave spectrum, and the aspect of the spectrum is lines. So at specific frequencies we see lines, either for absorption or for emission. For vibrations, what we call intramolecular vibrations, the spectral domain is the infrared, and we call it vibration or infrared. So there is a lot of experiments made with infrared emission or absorption, and we use that to know actually the vibration of molecules. And when we know the vibrations of molecules, we can know the molecule itself. You will see that. In electronic states, also the entity is a molecule, and it's in the visible ultraviolet side of the spectrum, and also it gives band aspect. Atoms, usually in atoms you just go from one orbit to another, so it's an electronic state change, and it's also in the visible ultraviolet regime. This part now, the absorption and transmission, is the practical part that I mentioned at the beginning. So I will stop this video here, and I will record another session with this part, after which I will immediately in the same video solve a few exercises on it. Thank you, and talk to you in another video.